The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
Thanks for coming. I know there's a problem set due. There's a quiz coming up on Thursday. We won't have lecture on Thursday, but we will have a quiz in the evening, and there will be a registration section tomorrow, which will be a quiz review. So today's lecture is the last of the lectures in the shortest path module, and unlike previous lectures, we're going to be talking about optimizations that don't change the worst case or asymptotic complexity, but improve empirical, sort of real-life performance, or potentially, and we can't prove this, but performance in the average case. And so we'll look at a couple of examples. The first one you've already done. You can optimize Dijkstra when you're looking for a single target. So implicitly, we've assumed that we're solving the single source, any or all destination problem when we've looked at the original Dijkstra algorithm and the Bellman-Ford algorithm. Many a time, you're going to have a source S, and you want to find the shortest path to a specific destination T, and you're doing this in your problem set, and you can do some optimization. Doesn't change the worst case complexity, but reduces runtime when you have a specific target, especially if the target is close to you and you don't have to traverse the entire graph. Obviously, the algorithm has to prove that the particular path that was chosen is in fact the shortest path from S to T, but it's a fairly straightforward modification, and I will go over it, but you're actually implementing it in PS6. We'll talk about bidirectional search, again, something you're doing from a standpoint of breadth-first search. How can you get from one source to a destination by doing bidirectional Dijkstra? And you can think of this as a frontier of shortest paths is being constructed from the source S forward, and this backwards frontier, you're following edges backwards, is being constructed from the destination. And effectively, when these two frontiers meet, you're going to be able to discover shortest paths. It turns out it's not as simple as what I just described, and so we'll have to look at that a little more carefully. So that is our single source, single target problem. We won't cover this in 006, but there's also this notion of all pairs shortest paths, which is something that 6046 covers. And that is something that says, well, I don't know what the source is. I don't know what the destination is. For any pair of vertices, find me the shortest path from S to T, given that pair. And so that, of course, is more work than even the single source all destination problem, because you're varying the source. All right? So those are kind of the three different shortest path problems, and we've looked at that, and we're going to look at this today, and we looked at it in the problem set, but we'll spend time specifically on this one and try and see if we can do some coding optimizations, if you will, to improve runtime. All right? So I emphasize that worst case complexity is unchanged for all of the Dijkstra versions that we'll be looking at today. So I want to put up pseudocode that you've written code for at this point, which is the Dijkstra pseudocode, because we'll take a look at it and modify it and execute it. So you have your set of vertices that you don't know the shortest paths to. So we do have initialize is going to set d of s to be 0 and d of u not equal to s to be infinity. And we have this set Q that we're going to process and continually extract the minimum priority from Q. And once we do that, we actually know the shortest path to U already. That's what the Dijkstra invariant is. And the process of extracting U implies that we have to do a relaxation step that updates the priorities and also modifies the parent pointers. So there's also the pi of V that is set to U, and as well as d of V getting decremented. Okay? So that's the Dijkstra algorithm. And one of the things that we can do, this straightforward thing, which is one line of code literally, is to say that if you know what the single target is, then you simply stop if U equals T. So no need to stop when Q becomes null, or you don't get to the point where Q is null. You stop when you've lifted off the T vertex from Q. All right? And so obviously this will run faster, assuming this check is a zero-time check. And that's really one instruction, so you can think of it that way. And you will basically run faster for sure when you have a specific target. It may be the case that your target is the last vertex that you find, and in that case, you run no slower. All right? So that's something that you've looked at. And that sort of takes care of the first optimization corresponding to single source, single target. Let's talk about something that's a little more interesting and non-obvious, which is the notion of bidirectional search. And in bidirectional search, what we have is we have S and we have T, and we have a bunch of nodes in between. Corresponding to this graph here. And what you do is you alternate search in the forward direction and the backwards direction. So you're going to do one step of Dijkstra, standard Dijkstra, which starts with S and goes forward. And so you can imagine that your forward search in the first step, you're going to pick the vertex S off of Q, and you're going to process the edges that come out of S, and that would correspond to these two edges. And so that's sort of one step of forward search going forward. And then you stop with the forward search, and you do a step of backward search. And so you go backward search, and I'll have to explain exactly what this means. Backward search from T, and the important thing is that you're following edges backward. So that means your data structure has to essentially have these edges that can be traversed in either the forward direction or the reverse direction. So that's something to keep in mind. But what would happen here simply is that your first frontier of backward search, T now in the backward search is the minimum priority. So we're going to have two priorities corresponding to S in the forward search, where that's a straightforward one. D of S equals 0, and we should think of it as D of F S equals 0, and we have D of B T equals 0, and these subscripts correspond to these two different priorities, and it's exactly complementary only the source S in the forward search has 0 priority at the beginning. Everything else has infinite priority. Only the target or destination has 0 priority in the backward search. Everything else is infinity. And you go forward, backward, and so on. And the question is, when do you stop? And we have to talk about that. And it turns out it's not a perfectly straightforward stopping condition, but it's something that will make sense, hopefully, when I get around to describing it. But having said all that, let's just put down all of the different data structures that we have to have. And it's kind of a doubling of the data structure, right? Because just like I doubled the priorities, I also need 2 different min priority queues corresponding to QF and QB. And as I said before, these edges have to be traversable sort of in the backwards direction. So this edge is in the graph goes this way, but you're going in the backwards direction as you're growing your backwards frontier. Okay? That's important to understand. So let me put down all of the specifics associated with these data structures. DFU correspond to the distances for the forward search, and DBU correspond to the distances for the backward search. Okay? And of course, we're going to have priority queues, plural, QF corresponding to the forward search, and QB corresponding to the backward search. And in initialize, as I said before, we're going to initialize DFS to be 0 and DBT equals 0, and then everything else, the DFs and the DBs are going to be infinity. All right? Okay, great. So that's what we have here. Now, first question. Roughly speaking, as I said, you can imagine intuitively that you're going to terminate the search when these frontiers meet. Okay? Clearly, you can't terminate it when these frontiers look like this. Okay? So that's the intuition. And you kind of seen that for the breadth first as well in your problem set. But in the context of Dijkstra, single source, single target, can someone tell me what the termination condition should be by looking at the code? I want a more specific or a more concrete termination condition that I can actually code up, as opposed to saying the frontiers meet, which, I don't know how to code. Okay? Someone else? All right, go for it.
When there's some node in, if you keep track of 2 different cost values, one from
the QF and the QB, that's correct. And some node.
If there's some node where the cost runs to get there from the start and from the end is finite.
Okay, all right. It's close. It's not quite something I can code up. Someone want to improve that? Someone want to improve that? I want something very, very specific. Someone? Go for it.
A node which has been extracted from both QF and QB?
The node which has been extracted from both QF and QB. So the reason I didn't quite buy your answer was the finite part is obviously correct, but I wanted a specific condition that says I'm going to do extract min. Just like I said, when I extract min and u equals t, I stop with the single source, single target. In the bidirectional case, I need to be pulled out a node from QF and pull out a node from QB, and then I get to stop. All right? So you get a cushion. You don't need to feel too bad because I think you already have a cushion. Yeah, I know that. I know everyone who has cushions. Right? Yeah. Actually, I don't, but I'm going to pretend I do. So the termination condition is that some vertex, and this is correct, some vertex U has been processed both in the forward search and the backward search. Okay, that corresponds to the frontiers meeting, but specifically, it's been deleted or extracted from both QF and QB. All right, so that's actually the easier question. There's a harder question, which is how do we find the shortest path after termination from S to T? Okay, and I should say specifically that, and I forgot to put this up, which I should, that we're going to have pi F and pi B, which are, this is sort of the normal data structure, and these are, the pi B is following the edges backward. So in some sense, the predecessor, so in the case of pi B, what you're saying is on this node here, which I'll call V2, for example, is if I'm going to choose this path here, and I need to get, obviously choose this edge here in any shortest path that gets to T, right? Because that's the only edge that goes to T. And so what I'm saying here is that pi, the predecessor pi BT equals V2. Okay? That makes sense? And then over here, if this was V1, then I would have pi F V1 equals S. Right? That makes sense? Everybody buy that? All right. So how do I find the shortest path from S to T after these frontiers have met and I've terminated this search? How do I do that? Someone? Go ahead.
Well, given that data structure, you start at your T, and you keep on going back to your current until you get to the point where they meet, and then you use the pi F to go from that node all the way back to S.
So so what I'm going to have to do is, but where do I switch is the question. Where do I switch from pi F to pi B? There has to be some point where I switch from, yeah, go ahead.
At the meeting point, I didn't know that was processed in both queues.
All right, was that what you were saying too? Okay, so so the claim is if W was processed first from both, or extracted from both QF and QB, then find the shortest path using pi F from S to W, right? So you can use pi F to get from S to W, and the way you do that is by applying pi F to W and then keep applying it until you get to S. Okay, this is normal search, right? Everybody knows this. You've coded it, so I hope you know it. And then we go find shortest path using pi B, right? And you're going to constantly apply pi B, and this is the backwards path from T to W. Okay. And this follows the edges backwards. All right? And this sounds pretty good. Everybody agree with this? Anybody disagree? Yeah.
pi b.
Yeah.
If pi b is given distance from t, shouldn't pi b be like pi b v2 equals t? Because v2 is
That's a good question. I might have gotten this wrong. So in the backward search, I need to. This can get pretty confusing. What do I have here? I want to follow the predecessor. You're exactly right. You're exactly right. Thank you. Thank you for pointing that out. All right. So what I have here is when I look at this path that goes this way, all right. When I look at the path that goes this way, V1 S is the predecessor of V1. V1 is the predecessor of, let's call this V3. V3 is the predecessor of V4. I'm just talking about the regular forwards path. We have S to V1, V1 to V3, V3 to V4, all the way to T, right? So what I have here is correct. The predecessor of V1 is S. The predecessor of V3 would be V1. So I could write pi f V3 equals V1, etc. Now let's just forget about the forwards path and let's just talk about the backwards path. In the backwards path, I want to be able to construct this backwards path. It's got to be the reverse of what I have, okay? And in that case, what I'm saying is that I want to move in this direction. So pretend that I've made the edges flip, okay? So in that case, if I pretend that this edge is like that, then, and if I just apply the regular predecessor relationship, then T is the predecessor of V2, and that's the point you're making, okay? T is the predecessor of V2, and so my apologies. I have pi b V2 equals T, and if I followed this edge here, then I'd have the appropriate relationship, but let's just stick to this one because that's the simple example. I don't quite know whether this edge is going to be part of my shortest path or not. It might be, and that's something that we'll compute, but what I have here is the predecessor relationship corresponding to the backwards edge, and so that's like flipping this edge, and hopefully that makes sense now. Thanks for pointing that out. What I wrote here, and so let's talk about what happens here. We know what happens in the forward search, and you've done that before. In the backward search, what happens is that I need to start according to this condition. Just like in the forward search, I found a W, and I continually applied pi of f to W. So this is apply pi of f to W, and then do pi of f W, and so on and so forth. And that's what you do in order to construct the shortest path. People buy that, right? And what I want to do here is apply pi b to W, and then pi b to W, and so on and so forth till I get to T, right? And this one till I get to S, right? So what I wrote here, S to W, T to W, there's nothing incorrect about that. And what's important to understand is the application of the pi f and the pi b, both, according to this, start with W, which is this vertex that caused the termination to happen. All right? So people buy this? Any other questions? All right, turns out this is not quite correct. And okay, this is not quite correct, right? And not because of the reason, because of this, the pi b inversion that I had before, right? So what have I said so far? It makes perfect sense. It says I have a vertex that caused the termination, and I'm going to call it W, okay? And that vertex is on the intersection of these two frontiers, okay? And I'm going to use that to construct the shortest path by constructing two subpaths using the forward pointers and the backward pointers, all right? So all of that makes sense, except it turns out that W may not be on the shortest path, okay? And I'll show you an example where W is not on the shortest path, right? So that's a real subtle condition. So we have to actually augment the termination condition, or we have to do something more than the termination condition. So I will tell you right away that the termination condition is correct, okay? And so the guy who got the cushion, deserved the cushion, okay? So the termination condition is correct. You are going to run Dijkstra, alternate forward search and backward search, and you're going to terminate when a particular vertex, call it W, is going to get pulled out from both QF and QB, all right? What is incorrect here is the use of W to construct the shortest path, all right? It turns out we have to do a little more work to go find the shortest path after we've terminated, and W may not be on the shortest path, all right? Any ideas as to what we might do? This is a bit of an unfair question, but certainly worth a cushion. How do you think we can fix this? If W is not on the shortest path, what do you think would be on the shortest path? Is there a way of finding this vertex so we can break this up? We absolutely have to use both pi f and pi b. There's no getting away from that, because these two frontiers have just sort of barely collided. The instant they've barely collided, we've stopped, okay? So we can't use pi f all the way from S to T. We can't use pi b all the way from T to S. These frontiers have just barely collided, okay? So what happens if W is not on the shortest path? Why is that the case? Yeah?
I just had a question. Are all the edge weights identical, or are they?
So the edge weights don't change. The edges are, there are no new edges. The way you want to think about it is that you can traverse the edges backwards, and so it's not like there are two edges here. Now you could fake it and have two edges with exactly the same weights over here. But are you saying that are the edge weights in the graph all identical across the edges, or were you asking about the forward search versus the backward search?
What I was asking is each edge weight the same in the graph?
No, they're all. We're using Dijkstra. The edge weights can be arbitrarily, but they're non-negative. Okay, so that's the usual Dijkstra requirement. They could be real numbers, they could be irrational numbers, they could be whatever, but they're all non-negative. All right. Now, in the backward search and the forward search, just to make that clear, while I've drawn this particular edge, that weight hasn't changed. Okay, that weight has better be the same. Okay. All right. So I'll show you an example, and we'll take an example of a fairly straightforward example. It turns out, it took a while to concoct this 5-node example that shows the idea here. But what we're going to do is take a look at the termination condition in a specific case where we're going to do this alternation of forwards and backwards search, and we'll see when it terminates as to what the correct way is to construct the shortest path. Right? And as I said before, the termination condition is correct. It's not like we stopped too early. When one of those nodes gets off from QF and QB, you get to stop. So that's my S over here, and I have a fairly straightforward graph. I have 5, 5, 3, 3, 3. So we don't need a computer program to tell us that the shortest path from S to T is the path with 3 edges that goes on top, okay, which has a weight of 9. All right? So this is the forward search. And I'm going to call all of these vertices names. So I have U, U prime, T, etc. Okay? So in the first step of the forward search, I'm going to be able to set, I'm sorry, this one is W. I'm going to be able to set dfw equals 5 and dfu equals 3. And obviously, df of s equals 0. and I'm not going to bother writing the infinities. It's just going to clutter up the board. All right? So stop me if you have questions on anything I'm writing here. So that's a forward search. Now, let's do the first step of backward search, right? Alternate, remember? Alternate forward search, backward search, forward search, backward search. And I'm just going to write this out again, so bear with me, because I think it'll be clear if you see this graph many times, as opposed to my erasing of what I've written. So I got S here, T there, U, U prime, W. And I'm going to hash this vertex vertically, because that's my backward search. And dB of T equals 0. Okay? And I'm going to follow this backwards and this backwards. And my weights are the same. It's the same graph. So I'm going to have D of B U prime equals 3. And dB of W equals 5. And I haven't seen U yet. I haven't seen S yet. And so all I've done is mark these two. All right? So far, so good? Again, stop me if you have questions. We got, obviously, a couple more steps to go here. And let's keep going. So now we do a forward search again. Yeah, that's fine. That's just hash that way, just to make sure. This is S, U, U prime, W, T. And what I have now is I'm going to process this vertex in the forward search, because I have a choice in the forward search to either pick W or U. This clearly has lower priority, because dFW equals 5. And dF of U equals 3. So extract min is obviously going to pick U, and it's going to process this edge now after extract min. And I'm going to have dF of U prime equals 6. Okay? Oh, there's 3 over there. Thanks. Good. So far, so good? Yep. All right. So now I go to the backward search. And again, I have S, T, U, U prime, W. I'm going to go ahead and hash this. This has been hashed horizontally. The hash horizontally means that it's been removed from QF. The hash vertically means that it's been removed from QB. And so when I look at this and I do a backward search, I'm going to hash this, and I'm going to set dB of U prime equals 3. And I have dB of W equals 5. So that I already had. And so when I have dB of W equals 5 and dB of U prime equals 3, then obviously I'm going to pick the one with the min priority, which corresponds to this one. And what it's going to do is it's going to go process that and set dB of U equals 6. All right? So what happened here simply was that I picked this vertex off of QB, because that was the min priority. And all I did was relax this particular edge in the backwards direction and set dBU equals 6. All right? Almost there. Any questions so far? Any bugs you noticed so far in what I've written? Yeah, back there, question. Okay, good. So people agree with this. All right, one more board to draw, and we'll be done. We would have terminated. All right, so getting pretty close. So I'm set up this way. Oh, shoot. Sorry. This is horizontal. So now I'm looking at it, and I want to do, I've taken care of these two, and I'm talking about the forward search here. So this is, again, the forward, and that's the backward. And now I'm doing a forward again. And my only choice now is to pick the W vertex off of QF, right? Because DF W equals 5, and this one has already been processed. DF of U equals 3, but I've hashed that. And so I've gone ahead and processed that vertex. And this one, DF of U prime equals 6. So if I compare in QF, I would be comparing U prime and W, and I would pick W. OK? People buy that? That's because I guess you buy the fact that 5 is less than 6, I hope. So that's what happens in this step of forward search. And when you go ahead and process this, you're going to set df of t to be 10. OK? And now you're starting to see why there may be a bit of a problem with our shortest path computation. All right, maybe. All right? Everything good? Right? So I've done, now what have I done here? I've removed W from QF. OK? I've removed W from QF. Right? Now let's look at the last step here of the backward search. ST. And so this was hashed, that was hashed. And if I look at what I have here, I have d b u prime equals 3, d f u prime equals 6. This was df w equals 5, db w equals 5, and so on and so forth. Again, you compare w, and you see that dbw equals 5, and df u prime equals 6. So therefore, you will pick w, OK? You will pick w and remove it from QF. So remove w from QF, all right? And process it. And what you end up with is df of s equals 10. OK? That's what you get because this is a 5, and that's a 5. OK? People see the problem here? What's the problem? Someone articulate the problem. Yeah, I mean, so what I have so far is I've terminated, but it looks like I end up with dfs. If I look from a standpoint of the forward weight, I get a 10 for t. I get dbt equals 10. If I look from a standpoint of the backwards weight, I get dbs equals 10. Okay? And we all know that the shortest path should be 9. Okay? So what happened here? Well, we terminated according to this condition. We terminated when w was pulled off from QF and QB, because that was the short path in some sense in terms of the number of edges, right? It was only of length 2. And so when the frontiers collide, this is the subtlety in the algorithm. The frontiers collide at some vertex regardless of the weights of the edges. Because we're alternating the forward search and the backward search, in effect, the frontiers are going to collide on the shortest length path. Right? That makes sense? Right? But so this example is set up so the shortest length path is not the shortest weight path. Okay? So we can't take the W and use pi f to construct part of the path and use pi b to construct the other part of the path and find the shortest weight path. we would get something incorrect, right? We would get a path of length 10 in this case if we did that. So how do we fix it? How do we fix it? One little termination condition doesn't change. How do we fix it? Someone? Back there. Or actually you. Alternate based on the weight. So exactly how would we do that?
So at each point you take the one that has the cheapest to go.
But that's what we're doing now, right? So we're in the so are you changing the alternation between the forward search and the backward search? You're saying that you're going to do more forward searches as opposed to backward searches?
If the overall cost is lower.
Overall cost is lower. You know, if you code that up, you get to keep this. That's I want a slightly different. I want a simpler fix, because I think what you're saying here, and I like the idea. I actually do like the idea. You're saying you're going to not do strict alternation, but you're going to do some sort of weighted alternation, from what I can tell, based on the weights. Okay, and I think there's an algorithm there that's correct. Okay, I probably won't be able to prove that it's correct to myself in 5 minutes, okay, or 10 minutes. But let's talk about that offline and see if there's a way. I'm a little worried that if you have, I don't know, positive rational numbers, and you got root 2 and square root of 2 and pi and the transcendental number corresponding to these weights, that this weighted alternation is going to be a bit hard to implement correctly. All right, but it's a neat idea. I would actually like to follow up on that. Something that's a little, yeah, back there.
You can look at the neighbors of all the nodes that are in your forward frontier and see if any of their neighbors are in the backwards frontier, and see if that's going to give you a shorter path than the one that you pulled out previously.
That's correct. That's almost exactly correct. I won't bother throwing it over, but this is yours. You want to catch it? You already have a cushion. All right. Suppose I just throw it, and anybody who wants to catch it gets it. How's that? Whoa. All right. I didn't hit anybody. Anybody who wants it, who doesn't have a cushion, right? We got all these cushions in my office and Eric's office. We got to do something about them. They're actually not that great. It was kind of a bit of an issue. I understand. We got to do frisbees next time or something, right? They're not. I mean, I can see why you're not enthusiastic about this, right? Okay. All right. So what the answer was in fact correct, and let me write it up over here. So we have to do a little more work. We terminate properly. We do the strict alternation, but we have to do a little bit more work. Okay. And the work we have to do is summarized very neatly by saying we want to find an x which is maybe different from w, possibly that has minimum value of d of x plus db x. All right, so we have to actually look, and this x is going to be neighboring, but we don't really need to specify that. What we say is we're going to have to look at qf and qb, and it's possible that w is the one that has minimum dfw plus dbw. But clearly that wasn't the case in this example. So in this example, w costs determination, but now we need to scan, and there's only two other vertices that are interesting here, which are u and u prime, and either of those will fit the bill, because we see that df of u plus db of u equals 3 plus 6 equals 9, and df of u prime plus db of u prime equals, I'm sorry, I should have put db here. db of u prime would be 6 plus 3 equals 9, right? So both of these are less than 10, and so we had to pick one of these as our x, okay? And if you pick one of these as our x, then at that point, we don't do w here, we do x. Okay? So this is, let me write it as x. It looks like a cross here. Right, so that's what happens. So the small little tweak, do the alternation, do the termination. Once you do the termination, go look and see if you can minimize the shortest path length by finding an appropriate x, which has the minimum sum of the forward and the backward priorities, and then you're in business. And then everything works. Okay? All right, great. So much for bidirectional search. Let me talk a little bit about heuristics that people use to modify the graph so things run faster in practice. So in particular, you can think about goal-directed search, or A star, if you've taken 6034, and there's some commonality between what I'm going to talk about here and that material. The basic idea is that we're going to modify the edge weights in such a way that you kind of go downhill towards the shortest path, and so the priorities are modified heuristically so things run a little bit quicker. You're trying to prune the search here. Okay. So we're going to modify the edge weights, and we have to be careful when we do this, obviously. We don't want to do things that are incorrect. But the way we're going to modify the edge weights is by having some sort of potential function that corresponds to lambda. And if the edge is between u and v, then we have an equation given a lambda that says the new w bar, is wuv minus lambda u plus lambda v. Okay? Now, we have to be a little careful here with respect to the choice of lambda. But the basic idea in terms of lambda is that suppose you have something like this, where you have a source vertex S, and you're again trying to do single source, single target going to T. And let's say you have an edge of weight 5 going out and an edge of weight 5 going out this way. Is there a way that you can guess that this is the edge that is more likely to be on your shortest path as opposed to this other edge, and increase the potential, or essentially increase the potential of this node, all right? So this node here may be the node T2, and this node may be the node T1. You want to increase the potential of node T2 such that you're actually trying to go uphill when you go this way, and this goes downhill. And that has the appropriate modifications on the edge weights such that the Dijkstra algorithm is steered towards going downhill and going down this path, and it terminates a little bit quicker. Right? Doesn't change asymptotic complexity. It just makes things run in practice a little bit faster if you choose the right potentials. Right? Feels like magic. How do you know how to increase the potential? What would you increase the potential for? What do you want to make things? What nodes do you want to make uphill? What nodes do you want to make downhill? So there's a bunch of questions. I'm not going to get into a lot of details, but I will tell you a couple of things. I'm going to give you really quickly a simple example that is both correct in terms of the actual shortest path you will get is the correct one, and a particular mechanism of modifying the potentials that uses landmarks. Right? So the way we are going to do this is by saying that any path WP is going to get modified based on its destination and source. So the only way that we can use the potential method is by ensuring that all of the shortest paths between any pair of vertices, we're only concerned about single source, single target here, but in general, it's a good thing to not change any of the shortest paths. So what used to be a shortest path should stay the shortest path. And the way you do that is by having a potential function that if you have an arbitrary path, essentially, and this is a path from S to T, that you subtract out something based on a function of the vertex. In this case, you have S, and in this case, you have T. So the nice thing is that any path from S to T is going to get shifted by the same amount corresponding to this additional term here. So what that means is that the final shortest path that you discover will be the correct shortest path. You just may hopefully discover it faster. All right? So that's the correctness check. And I'll put this in the notes, or maybe TAs can cover it in the section. But one way of getting these potentials, or this potential function, is to use what's called a landmark. And so the basic idea is that you have a landmark L, which is a vertex belonging to V, and we're going to pre-compute delta of U comma L. So for any input vertex, you want to find the shortest path to this landmark. So it's like change the source, but the destination stays the same. And the potential, lambda T U, is defined as delta of UL minus delta of TL. Okay? So you have a source S, you have a destination T, and now you have a landmark L. I'm going to pre-compute delta UL for all U belonging to V, and I'm also going to pre-compute for a given T a delta TL. So that's just a single T, so that's just one computation. This one is much more computation. And if I use this potential, you can show that it's correct using the triangle inequality. And this is now a heuristic. With the correct choice of landmark, Dijkstra empirically will run faster. So if you know for sure that you need to go through Middle America to get from Caltech to Boston, and in particular, there's one particular landmark you want to go through Texas or something, and you pick Austin, Texas, then you could do this computation, and maybe Dijkstra runs 2x faster, 20% faster. All right? I'll put the argument about correctness and the specifics of these things in the notes, and you can take a look at it offline.